Hi everyone, welcome to part 2 of lesson 9.1 and 9.4, vectors. Today we're going to start off by talking about magnitude. So let's see what magnitude is. The magnitude of a vector is its length. It tells how long a vector is. Now magnitude can represent speed or velocity. So there are other applications where magnitude would represent another quantity, but for our purposes right now, magnitude is length. Now, we base it on the two components, the horizontal and vertical component. Notice if I wanted the length of this makes a right triangle, so I can just use the Pythagorean theorem. 2 squared plus 3 squared equals the magnitude squared. And when you solve for the magnitude, you would just do a square root. So I get this formula here, and if I'm working in 3 dimensions, I would just add a z on here. X squared plus y squared plus z squared, and do the square root. Now, the symbol for magnitude looks like absolute value symbols. It's the name of the vector inside those symbols. Let's take a look at some examples. In the first example, they want us to find the magnitude of each vector, and they've given us 3 different vectors here. So see if you can apply the formula, and then press play to see if you're right. So for the first vector, I did 2 squared plus negative 3 squared. And you need to be careful about these parentheses. When you square a negative, it turns positive. But if you put in the negative 3 squared without the parentheses, you'll get negative 9. So be very careful. A lot of times when I'm squaring a negative, I don't even type the negative sign because I know that when I square it, it's going to turn positive. So when I calculated this, I got the square root of 13. This is the magnitude of vector u. For part B, vector v, I did 5 squared plus 0 squared, and it's the square root of that. When you square the 5, you get 25, but 0 squared is just 0, so it's just the square root of 25, which is 5 again. Now, magnitude is a length. You can't get the positive or negative result from any of these square roots, because length has to be positive. In part C, we're given the fractions 3/5 and 4/5. Now, when you square them, you get 9 over 25 plus 16 over 25, which is 25 over 25, which reduces to 1. So the square root of 1 is 1. So that's it for these examples. Let's do some in 3 dimensions next. So they want us to find the magnitude of these 3 vectors, vector u, which is 3, 2, 5, vector v, which has component form 0, 3, negative 1, and vector w, which has component form 0, 0, negative 1. So see if you can find those magnitudes, and then press play to see if you're right. So the magnitude for vector u, I did 3 squared plus 2 squared plus 5 squared, and the square root of that. And you get the square root of 38. Now this can't be simplified, so I can just leave it like this. The magnitude of vector v, you get 0 squared plus 3 squared plus negative 1 squared, which comes out to the square root of 10. And the magnitude of vector w is 0 squared plus 0 squared plus negative 1 squared, which comes out to positive 1. So that's it for magnitude. Next, we're going to take a look at unit vectors. You may remember in the first video, I told you a unit vector is a vector with a length of 1. Well, the most common types of unit vectors are ones that only go in one direction. They only have a horizontal component or a vertical component. So we can use these unit vectors to help us rewrite the component form in terms of the unit vector. So vector I is the unit vector 1, 0. It only has a horizontal component. Vector J is the unit vector 0, 1, which only has a vertical component. And they're going to be of a length 1. If I'm working in 3 dimensions, I would use 1, 0, 0 for the horizontal component. J would be 0, 1, 0 for the vertical, and K would be 0, 0, 1 for that extra Z variable. Okay, so when I have a vector, I can write it in terms of these unit vectors simply by taking the component and multiplying it by the unit vector that represents that particular component. So A was in the X position, which means that I would take the component form up here that has a 1 in the x position and use that. So I would use vector I. So I would take whatever number was here and multiply by I. So it's AI. Okay, and then B was in the y component. So that's the j vector up here. So I would write bj. So to rewrite this vector using the unit vectors, I would simply write AI plus bj. So I've written it in terms of addition because if I add this unit vector times A plus this unit vector times B, I will get this component form. Let's take a look at some examples. In part A, they want us to write the vector u, which is component form 5, -8 in terms of I and j. And in part B, they want us to write the vector u, which is 5, -3, 6 in terms of I, j, and k. So see if you can do that and then press play to see if you're right. So all I needed to do was take this 5 and multiply by I, so I get 5i, and take this 8 and multiply by j, so I had -8j. So the way I remember the order of this is the abbreviation, I'm just kidding. Ha ha. So all I have to do is take each of these and put the I, j, and then if there's a third component, I would write a k here. So this becomes 5 minus 3j plus 6k, and that is my new vector. So let's take a look at another example. In this example, we're taking some vectors that have been written in the form of those unit vectors. We're going to do some arithmetic with them. So we might add them or subtract them or multiply by scalars. Now, personally, I like this better than the arithmetic we did before because we're more used to seeing things in these terms. Let's take a look at part A. They said if u is 3i plus 2j and v is -i plus 6j, we have to write 2u plus 5v in terms of I and j. And in part B, it says if u is 2i plus 2j minus 3k, and v is 4i plus 7k, we have to express the vector 2u plus 3v in terms of I, j, and k. So basically all we have to do is take vector u and put it in where u is. So put parentheses here and input the vector u right here. And same thing for v. So we have to do that in both of these questions. And then all we do is we simplify those expressions. Combine any like terms, do some distribution, and you're done. So try and do that and then press play to see if you're right. So what I did is I wrote out the multiplication. If you do 2 times u, you get 6i plus 4j. If you do 5 times v, you get -5i plus 30j. Then I just have to combine the like terms. 6i minus 5i is 1i, and 4j plus 30j is 34j. In part B, again, I wrote out the multiplication, so I distributed into each vector, and then I combined the like terms. I got 16i plus 4j plus 15k. So next we're going to take a look at direction. Direction of a two-dimensional vector is measured off of the positive x-axis. And we always pretend that the initial point is at the origin, or 0, 0. So we need to measure the distance counterclockwise, just like we did on our unit circle, from the positive x-axis to our vector. Now we do that using the tangent function. And what we can do with direction is if we know the direction and the magnitude, we can then find the component form of our vector. So if I know the magnitude and I know the direction of my vector, what I can do is do the magnitude times the cosine of that direction, and that will get me my x value, my horizontal component. And if I do my magnitude times the sine of the angle, that will get me my y component, or the vertical component. And that should make sense because in the past, cosine represented an x value and sine represented a y value. So that's why we use them for horizontal and vertical components. Now, if I wanted to write it in terms of the unit vectors, I could do the magnitude of v times the cosine of theta, I, plus the magnitude of v times the sine of theta, j. And that would get me that in terms of the unit vectors. Let's take a look at an example. In this example, it says a vector v has length 8 and direction pi over 3. Find the horizontal and vertical components and write v in terms of I and j. Now, for this one, you have to use your unit circle to get exact values for pi over 3 and use those formulas that we just talked about. We have magnitude and direction. So use the formulas we just talked about and then press play to see if you're right. So what I did is I did the magnitude times the cosine of pi over 3 times I plus the magnitude times the sine of pi over 3 times j. Cosine at pi over 3 is 1/2. Sine at pi over 3 is the square root of 3 over 2. And then I just simplified. Half of 8 is 4, and 8 over 2 reduces to 4 times the square root of 3. So this is my final vector. Let's take a look at another example. In this example, they want us to find the direction of vector u, which is negative square root 3i plus j. So what I've done is I've written out 2 steps for you. The first step is to draw the vector on a coordinate plane. Now, we do this so that we can tell which quadrant we're in, because remember, we need to measure off of the positive x-axis in a counterclockwise direction. So if we find out where the vector is, that will help us, because if we just blindly do inverse tangent, we might get a wrong angle, because if we're in quadrant 2, 3, or 4, it's not going to be accurate. Generally, inverse tangent gives us a quadrant 1 angle. So we need to be very, very careful. So you draw it, and then use the tangent to find the reference angle, and then you use your knowledge to figure out what the actual angle is. So try and do those steps, and then press play to see if you're right. So when I drew my vector, I went negative square root 3, and then up 1. So this was horizontal and vertical. Now I can use my inverse tangent. Inverse tangent, I wanted this angle here, inverse tangent of 1 over square root 3. And I got approximately pi over 6. Okay, now that is given in radians. If you got it in degrees, it would not be pi over 6, it would be 30 degrees. And that's okay. But normally in our book, we're going to be working in radians. So try and give the radian value. Now, pi over 6 is a first quadrant angle, but this is obviously a second quadrant angle. So what I need to do is find the reference angle, the actual angle from the positive x-axis all the way around to here. And that comes out to be 5 pi over 6. So when you're dealing with direction, you might want to keep your unit circle close at hand. We still need to talk about direction angles for a 3-dimensional vector, but I think we'll do that in the next video. So make sure you watch that one.